Welcome to the video homework for topic 4.4, Aromaticity. Recommended reading before attempting the problems in this homework come from Lesson 4.4 in the Organic Chemistry 2 Primer 2018 by Professors Tennyson, Houjeiry, and Smith. We've learned in this lesson of the primer that aromaticity endows a system with a great deal of additional stability as compared to an isolated alkene. And for that reason, aromatic systems will undergo different reactions than will isolated alkenes, and it's very important for us to be able to identify then which systems are aromatic and have that extra stability and which are not. So this question simply asks us to label each of these potential structures as being aromatic, to label with an A, anti-aromatic, which we would label AA, or non-aromatic, which we will label with an N. For the aromatic molecules, this question asks us to highlight the aromatic pi system. We should just circle it here, and we'll provide the number of electrons in the pi system. And the number of electrons in that pi system is very important in our analysis of whether the compound is aromatic or not. Because if we look at the criteria for aromaticity, we have to have an uninterrupted pi conjugated system all the way around a ring, and that pi system has to have 4n plus 2 electrons in it, where n is some integer. Anti-aromatic systems, on the other hand, also have to have an uninterrupted pi system around a whole ring, but only 4n electrons rather than 4n plus 2 are present in the anti-aromatic system. And n non-aromatic systems would refer to any other case beyond what we've defined for aromaticity or anti-aromatic systems. One easy check to see whether your compound has an uninterrupted pi system around the whole ring would be to attempt to draw resonance structures. If you can draw resonance contributors wherein every atom in the ring in one of the resonance contributors has a pi bond going to it, then you've identified an uninterrupted pi system around the entire ring. So in this first compound, for example, we can draw a resonance contributor that looks like this, and upon doing so, we see that these two atoms in the ring already have pi bonds going to them in the initial structure, and in our additional resonance contributor we have pi bonds here. So if we were to draw a resonance hybrid, we would have a hybrid that looks like this, where there's pi bond character in each of the three positions around this triangle-shaped ring. Now that means that we have an uninterrupted pi system around the ring. That is one of the criteria for aromaticity, but we also have to make sure that that pi system contains 4n plus 2 electrons, where n has to be an integer. So we would have to count the number of electrons we can move around the ring. We can move these two pi bonding electrons, and there are no lone pairs to move, so we only have moved a total of 2 electrons in that case. So we have to solve for n. 4n plus 2 equals 2, and if n is an integer when we solve for it, then this is an aromatic system. It has this Huckel's rule number of electrons. And if we solve for this, n equals 0, then 0 plus 2 equals 2. So this has 2 electrons in its pi system, we've indicated here, and this is aromatic. And the pi system would be all the way around the ring if we do the part of the problem asking us to highlight that. If we move on to the second example, we can draw an additional resonance contributor that looks like this, where we move the pi bond here, and there's a plus charge here, but there's no way to engage this carbon in resonance because it has 4 sigma bonds and it's an sp3 hybridized carbon. So this does not have an uninterrupted pi system around the ring, and it can then neither be aromatic nor can it be anti-aromatic. In our third case, we have the potential to draw a resonance contributor where we move this pi bond like this, or we could move the pi bond, like this. And we can move the pi bonds then around the whole ring, and if you were to draw the resonance hybrid after figuring out all of the resonance contributors, you would have a structure like this where there's a plus charge delocalized around the whole ring. So this has an uninterrupted pi system. Now how many electrons can we move around the ring to be in that pi system? Well, we have 2 pi bonds, and each bond is 2 electrons, so that's 2 times 2. So we have 4 electrons there. The positive charge will move around the ring, but remember that the positive charge is not a pair of electrons. The positive charge is just a formal charge on the atom. You don't move electrons with that. So we only have 4 electrons to move around. If we solve for 4n plus 2 equals 4, we would get N equals 1/2. That's not an integer, so that means that this molecule is anti-aromatic. If we move on to our fourth case, it reminds us, hopefully, of this second case where if we identify that one of the carbons in this ring is an sp3 hybridized carbon with 4 sigma bonds, there's no way that that atom can make a pi bond because it is sp3 hybridized. So that's going to simply be non-aromatic. And finally, we get to our last case. We see this cation with this 7-membered ring with these 3 pi bonds. We can draw our resonance contributors where we've moved these pi bonds all the way around the ring. So the resonance hybrid would have the electrons delocalized around the whole ring with a positive charge in the structure. And the number of electrons we move around would be 2 electrons for each of those pi bonds we moved, 2, 4, 6. So if we look to see whether that is a correct number of electrons for aromaticity, 4n plus 2 equals 6. We solve that for n equals 1. That's an integer, and that means that this is aromatic, and it has 6 pi electrons in that pi system. And the other part of the question was asking us to highlight the pi system. And of course, the pi system is all the way around those atoms. We have the same question on this next slide, but instead of having cations to consider, we have a series of anions to consider. Aromatic compounds may be neutral, cationic, anionic. There's no requirement in the criteria for the charge. The criteria just has to do with how many pi system electrons we're able to move around the ring and whether it's uninterrupted. And since these are anions, we have to take a closer look at what an anionic carbon looks like. Carbon with a minus charge on it has a lone pair, so you should draw those in, especially when we are considering the importance of counting the number of electrons we move around a ring to check and see whether it's going to be an aromatic compound or not. Now let's consider the first case in a little more detail. We would be able to, if we drew all the resonance contributors, we could draw a hybrid where we have a structure that looks like this. So there is an uninterrupted pi system around the whole ring. So then we just need to check for the number of electrons. Well, we only have a pair of electrons and a pi bonding pair to move. So 1 lone pair and 1 pi bond, that's 2 electrons for each. We would be able to move a total of 4 electrons. 4 electrons equals 4n electrons if n is an integer, not 4n plus 2. So 4n, when n is an integer, corresponds to the number of electrons for an anti-aromatic system. So we'll label this as being anti-aromatic. The next compound here has this sp3 hybridized carbon. We can't engage that carbon in the pi system because an sp3 hybridized carbon can't make a pi bond. So this is automatically a non-aromatic compound. Now if we look at our third case, this is a pretty interesting case. You should consider this one a little bit more carefully as you prepare for the next worksheet. You have a lone pair on the negatively charged carbon, of course. You will move that in your resonance structure to make a pi bond here, push this pi bond away to make a pi bond here, push this pi bond away to make a negative charge on this carbon. So we could have a resonance hybrid where we delocalize electrons all the way around the ring, and there's a negative charge delocalized across all those carbons as well. So that has an uninterrupted pi system. We next have to check how many electrons are in that pi system. We have the lone pair and 2 pi bonds. So we have 3 pairs, that's 6 electrons. And if we try to solve for 4n plus 2, n equals 1. So 6 is a 4n plus 2 number of electrons when n is an integer. That is an aromatic system. And of course the pi system will be all the way around the ring. We're asked to highlight that, and we would have 6 electrons in that pi system. If we look at the next structure, we will identify an sp3 hybridized carbon that is not capable of contributing to making a pi bond around this ring for delocalization around the ring. So this is a non-aromatic system, similar to what we saw over here for the second case with an sp3 hybridized carbon down at this corner. And then we get to this last case. And if you start to draw your resonance structures, you could draw contributors like this. You'd be able to get a resonance hybrid that looks something like this. And you'd say, well, that is an uninterrupted pi system. I've moved a pair of electrons here and 3 pi bonding pairs. So I've moved 4 pairs total. That's 8 electrons. And 8 electrons equals a 4n number of electrons when n equals 2. So that would be an anti-aromatic species. Now we're making the assumption that all of these systems are planar. You have to have the system be planar to have uninterrupted pi conjugation around the ring. For rings that are larger than 6, they are flexible enough to bend out of planarity even if there are pi bonds. So this would actually not be planar and would actually be a non-aromatic compound, because anti-aromatic would be less stable than non-aromatic. Let's consider a case where some of the carbons are replaced with other heteroatoms, such as nitrogen. Nitrogen with only 3 bonds drawn to it has a lone pair of electrons as well. So we should fill those in if we know that part of our important task is going to be counting electrons. A nitrogen atom can donate its lone pair, just like a lone pair on a carbon could be donated. So in this case, I could move 4 electrons around the whole ring, and you'd expect that to be anti-aromatic if that happened. In the case of this compound, which is called perol, you can move these electrons all the way around the ring, and in doing so you've moved 3 pairs of electrons, 1 lone pair and 2 pi bonding pairs. So you've moved a total of 3 pairs, that's 6 electrons, and that corresponds to an aromatic number of electrons. And those electrons would be delocalized all the way around this 5-membered ring as that lone pair of nitrogen is donated, similar to what we saw in the previous problem where we had delocalization around a 5-membered ring with a lone pair on carbon. Now sometimes students become a little bit confused when they see a compound with a nitrogen that has both a lone pair and a pi bond going to it. So, well, do I move the lone pair and the pi bond? Do I move just the pi bond, just the lone pair? And that's a very important question because it is imperative that we get the right number of electrons to know whether we have more or less stability than what normal alkenes would have. And if you already have this nitrogen with a pi bond, you would not need to use the lone pair to make a pi bond. So it's already got a pi bond, you can use that in the resonance. That's different from this nitrogen over here. There wasn't a pi bond, so in order to get it to be involved in the pi system, you needed to use this lone pair to get a pi bond in the next resonance contributor to that nitrogen. This nitrogen already has a pi bond, so you don't need to use its lone pair. Its lone pair will stay right where it is. This nitrogen at the top, though, does not have a pi bond yet. You will have to move the lone pair in order to establish a pi bond in the next resonance contributor, which would look like this. So you've moved the lone pair out onto the carbon atom here, and then you could draw additional resonance contributors to find various other structures. So we're able to move 1, 2, 3 pairs of electrons, that's 6 electrons, all the way around the ring. So that is an aromatic compound. Similarly, in the 6-membered ring called pyridine, you have a lone pair in the nitrogen, but that nitrogen already has a pi bond. So you don't need to use this lone pair to make a pi bond to this nitrogen for it to engage in the pi system. So if I'm going to draw a resonance around the ring, I don't even mess with that lone pair. I have a resonance structure that looks just like what we'd have for benzene if this was a CH. Look just like benzene then. And it behaves the same way. You've moved 6 electrons around the whole ring, and it's an aromatic compound. And we can highlight the pi systems in these molecules all the way around the ring to show where the aromatic part of the molecule is. This next molecule is relatively easy because the nitrogen isn't even in the ring. This is just a benzene ring that happens to have a nitrogen on the outside. And sure, you can draw resonance contributors where you push the lone pair into the ring, but that doesn't have anything to do with the fact that this ring itself is aromatic. So we've moved 6 electrons around the ring. Remember, it is the ring system, not any appended substituents that we're worried about when we're talking about identifying aromaticity. And not every atom in the whole molecule has to be part of the pi conjugated system that makes this aromatic. It's just the atoms that have the pi system around the ring. An aromatic compound can, of course, have substituents. And then we have a compound here that should remind us of a lone pair in a 7-membered ring with 3 pi bonds that we saw in the previous. And just like in this previous problem, we should identify that, well, if I moved all those electrons around in that way, I'd have 8 electrons, and that would be anti-aromatic. But because I have a ring that is greater than 6 atoms in size, it's going to be flexible enough to just twist out of planarity to avoid the instability of an anti-aromatic arrangement of electrons. So going back to this compound that has the nitrogen with the lone pair there, we would say, well, this is going to be non-aromatic. Nitrogen is not the only heteroatom that one can observe in aromatic systems. So in this last problem for this homework, we see a series of molecules where I've put borons or oxygen or sulfur, nitrogen, phosphorus, a variety of different heteroatoms that may have lone pairs or not. And the presence of unusual atoms doesn't fundamentally change how we approach the problem. We have the same criteria, and we're simply trying to see whether we have the correct number of electrons in a ring system's pi system to endow this with added stability for aromaticity, or if it makes it less stable, in which case it would be anti-aromatic. So if we look at these and evaluate the periodic table and figure out lone pairs, you'd see that oxygen with 2 bonds has 2 lone pairs. Sulfur also has 2 lone pairs because it's in the same group as oxygen. Nitrogen has 1 lone pair. Phosphorus is in the same column as nitrogen, and it has 1 lone pair as well. Now boron is this case where it is an sp2 hybridized atom with an empty p orbital. It does not have a lone pair. And it only has 6 electrons in its valence shell. So I can draw a resonance structure where I move electrons towards the boron, and then the boron would obtain an octet like this. And I'd be left with a positive charge on the carbon and a negative charge on the boron. But we can draw the resonance contributors around the ring, and that allows us to delocalize the pi system around the whole system. So hypothetically, our resonance hybrid would look like this, and you might have some partial negative charge on the boron and some partial positive charge on the carbons. So we've delocalized these electrons around the whole ring, and we have to check how many electrons we've moved. Well, we only moved the pi bonding electrons because the boron does not have a lone pair to move. It's just got an empty orbital into which those pi bonding electrons can donate. So 2 electrons in the pi system equals 4n plus 2 when n is the integer 0. So this is an aromatic system. And of course the pi conjugated system is all around this 3-membered ring, not the hydrogen at the top. Another challenging problem for some students that confuses them a little bit is, well, what if an atom has 2 lone pairs? Should I move both of those? Should I move one? What do I do? Well, you're going to approach the problem the same way you did with the nitrogen problem. If I need to use the lone pair to make a pi bond, I'll move it. If I don't need to move the lone pair to make a pi bond, say an atom already has a pi bond like this phosphorus does, I wouldn't need to move the lone pair to engage that atom in the pi system. It's already engaged in the pi system through a pi bond. This oxygen, in this specific example, does not have a pi bond going to it yet, but you can draw a resonance contributor where one of the lone pairs is used to make a pi bond, and then I can move these around the ring and dump that lone pair onto a carbon. Now you'll see, once I use that lone pair to make a pi bond, it already has a pi bond. Then I wouldn't need to move the second lone pair. You only move one to make one pi bond. That's all you need to engage the atom in the pi system. So you see in this problem that we moved 1 lone pair and 2 pi bonds. That's 3 pairs of electrons total. We used 3 arrows. So that's 6 electrons, and that's the same number as benzene, which we've seen in a few cases already leads to an aromatic system. This next ring has 2 different heteroatoms in it, a sulfur and a nitrogen. The sulfur needs to use a lone pair to help it make a pi bond in one of the resonance contributors. But when we get to the nitrogen, it has a lone pair, but it already has a pi bond. So we're going to move the pi bond. We don't need to mess with the lone pair. So we've had to move 1 pair, 2 pairs, 3 pairs of electrons. So we've moved 3 pairs, that's 6 electrons. So that would also be an aromatic compound. Pi systems encompass all the atoms in the ring in both those cases. And now we get to the phosphorus containing ring over here. The phosphorus has this lone pair, but we're not going to have to move that lone pair. We already have a pi bond going to that phosphorus atom. So if we move those pi bonds around the ring, every atom in the ring already has pi bond going to it. That's 6 electrons, and that's an aromatic number. Finally, I have one case here where you see 2 rings that are fused together. Well, you don't really care if 2 rings are fused together or not. I need to identify one big ring around which I have pi conjugation, which I can highlight here for clarity. So I can draw a resonance where I push electrons all the way around this big outer ring, and I kind of ignore that middle piece in the middle holding those 2 rings together. Now if I do that, and count up how many electrons I've moved 1, 2, 3, 4, 5 pairs of electrons. So I've moved a total of 10 electrons around the ring. if I try to solve 10 equals 4n plus 2, maybe it's aromatic, 10 equals 4n. I need n to be an integer. If n equals 2 here, n equals 2.5 here, well, it's not an integer if I check to see if it's anti-aromatic, but n is an integer when I try to plug 10 into the Huckel rule aromatic equation. So this is an aromatic system.